Good afternoon to one and all present here. I am B. Nagarani, Assistant Professor, Department of Mathematics, SRMVEC Engineering College. Today I am going to discuss about the topic Laplace transforms. The topics are going to be discussed are Introduction to Laplace transforms, definitions, standard results, properties of Laplace transforms, and problems based on properties. Laplace transform was introduced by the French mathematician Pierre-Simon Laplace. Introduction. Transformation in mathematics deals with the conversion of one function to another function that may not be in the same domain. Laplace transform is a powerful transformation tool which literally transforms the original differential equation into an elementary algebraic expression. This later can then simply be transformed once again into the solution of the original problem. So this transform is named after the mathematician and renowned astronomer Pierre-Simon Laplace, who lived in France. Laplace transforms was first used by the French mathematician Pierre-Simon de Laplace in 18th century. Laplace transform has wide applications in engineering fields like network analysis, control systems, circuit theory, and many other areas. So as I already told that the Laplace transform is nothing but the conversion of time domain to frequency domain. This is the mathematical definition of Laplace transform. Let f of t be a function defined for all t greater than or equal to 0. Then integral 0 to infinity e power minus st f of t dt is defined as the Laplace transform of the function f of t if the integral exists. And it is denoted by the notation L of f of t or f of s. So L of f of t is equal to integral 0 to infinity e power minus st f of t dt is equal to f of s. Now the sufficient conditions for the existence of Laplace transform. Let f of t be a function defined for all t greater than or equal to 0 such that f of t is piecewise continuous in the interval 0, infinity and f of t is of exponential order. Then the Laplace transform of f of t exists for s is greater than alpha. So here we see that some of the functions and their Laplace transform results. First one, if the function f of t is equal to 1, then its corresponding Laplace transform solution is f of s is equal to 1 by s. And for f of t equal to e power at, it is f of s is equal to 1 by s minus a. And for the function f of t equal to t power n, the corresponding Laplace transform of the function t power n is n factorial by s power n plus 1. And if it is sin at, its corresponding Laplace transform is a by s square plus a square. And for cos at, it is s by s square plus a square. Similarly, if the function f of t is equal to sin h at, the corresponding Laplace transform is f of s is equal to a divided by s square minus a square. And for cos h at, it is s by s square minus a square. Similarly, we can find the corresponding Laplace transformation for any function. So here we see that the derivation of the Laplace transform of a functions. For example, first one, if the function f of t is equal to 1, after applying the Laplace transform, the result becomes 1 by s. This will be obtained by the definition of Laplace transform. Here L represents the Laplace transform. So we know that the definition of Laplace transform is L of f of t is equal to integral 0 to infinity e power minus st f of t dt. So here in this definition we just replace the function f of t by 1, and after that taking integration with respect to t and applying the limits, we got the result. So here the function is e power minus st. When we integrating e power minus st with respect to t, the integration is e power minus s into t divided by the coefficient of t, that is minus s, and applying limit 0 to infinity. So when we applying the limit for t, when we apply the upper limit infinity for t, we get e power minus infinity. So e power minus infinity is nothing but 0. So that when we apply the upper limit, it becomes 0. Then minus of lower limit is 0. So when we replace a t by 0, we get e power 0. E power 0 is nothing but 1. So 1 by s. So totally minus 1 by s of 0 minus 1, it becomes 1 by s. So this is the way how to find the derivation of a particular function. Similarly, in the second problem, we see that the function f of t is nothing but e power at. The same process will be applied in the definition of Laplace transform. Just to replace f of t by e power at, and after taking integration, we got the result as 1 by s minus a. And similarly, for the function f of t equal to e power minus at, the result becomes 1 by s plus a. And for t, if the function is t, the result is 1 by s square. In general, for the function t power n, after taking Laplace transform, the result becomes n factorial divided by s power n plus 1. And similarly, for the function f of t equal to cos h at, we need to find the Laplace transform for the function cos h at. First of all, we can rewrite the hyperbolic function cos h at using the exponential formulas e power at plus e power minus at divided by 2. We know that cos h theta equal to e power theta plus e power minus theta divided by 2. So here we see that in the place of theta we have a into t. So just replace in the formula theta by at. So here cos h at can be rewritten as e power at plus e power minus at divided by 2. After that, applying the linearity property, just we can take outside the term the number 1 by 2 from the Laplace transform, because if you take Laplace transform for a constant, it becomes again a constant only. So that just to bring 1 by 2 outside from the Laplace transform. So 1 by 2 into L of e power at plus L of e power minus at. So we know that by the previous slide, we see that the Laplace transform for the function e power at is 1 by s minus a, and for Laplace transform of the function e power minus at is 1 by s plus a. Just applying here and taking simplification, we get the result or Laplace transform for the function cos h at as s by s square minus a square. Similarly, we can find the corresponding Laplace transforms for various functions. And this is also another example. Find Laplace transform of the function 3 into e power 5t plus 5 into cos t. So here we see that there are two functions. So we can apply linearity property, which means we can apply Laplace transforms each and every term. So first 3 into e power 5t, when we apply Laplace transform, bring 3 outside from the Laplace transform because 3 is a constant. So 3 into L of e power 5t plus, similarly 5 is constant. So 5 into L of cos t. After that 3 into, we know that Laplace transform of e power at is nothing but 1 by s minus a. So here a is equal to 5. Here a is equal to 5. So the result is 1 by s minus 5. So therefore 3 into 1 by s minus 5 plus 5 into, again we know that the Laplace transform of the function cos t is s by s square plus 1. That is the Laplace transform of cos at is s by s square plus a square. Here we get a is 1, so that the result becomes s by s square plus 1. So therefore finally the result, the solution for this problem is 3 divided by s minus 5 plus 5s divided by s square plus 1. Similarly, the next problem, second problem, we see that L of t square plus e power minus 5t plus 8 plus sin h 5t. So here we are having 4 different functions in a single problem. So here also we can apply the technique of linearity property, which means we have to apply Laplace transform for each functions. Laplace transform for each functions, so that it becomes L of t square plus L of e power minus 5t plus 8 into L of 1, because 8 is constant, let us consider as 8 into 1, so 8 into L of 1 plus L of sin h 5t. So by the previous table, we directly substitute the results or solutions of Laplace transform of the corresponding functions. So for that, L of t square means t power n. We can apply the formula t power n. So t power n is nothing but n factorial by s power n plus 1. So here n is equal to 2. Therefore, the result of Laplace transform of t square is 2 factorial by s cube, and L of e power minus 5t is 1 divided by s plus 5. 8 into L of 1, that is 1 by s, plus L of sin h 5t is a divided by s square minus a square. Here a is 5, so that 5 divided by s square minus 25. So this is the way how to find the Laplace transform for different functions. So more number of examples. Here we need to find the Laplace transform of the function cos square 2t. So before directly applying Laplace transform, first of all we have to rewrite the function in a simple way. So cos square 2t can be rewritten as 1 plus cos 4t divided by 2. This will be obtained by using the formula cos square theta is equal to 1 plus cos 2 theta divided by 2. So here in the place of theta we have 2t. So the formula is 1 plus cos 2 theta. So that 2 into 2t, therefore 4t. So therefore this cos square 2t can be rewritten as 1 plus cos 4t divided by 2. And again here we see that there are two functions. So we can applying Laplace transform separately for those functions. So it becomes 1 by 2 into Laplace transform of 1 plus Laplace transform of cos 4at. So we know that Laplace transform of 1 is 1 by s, and the Laplace transform of cos at is s by s square plus a square. Here a is 4, so it becomes s by s square plus 16. After taking small simplification, LCM etc. like that, we got the result as s square plus 8 by s into s square plus 16. So this is the solution for the function cos square 2t after applying Laplace transform. Similarly, the next problem, find L of sin 2t into sin 3t. Here we see that there are two functions but in product. So first of all, we need to break the product functions into addition of terms. For that we have to use some other formula, trigonometric formula. So this is of the form sin A sin B. So sin A sin B means we have to use the formula 1 by 2 into cos of A minus B minus cos of A plus B. So that here A is 2t and B is 3t. When we subtract this 2t minus 3t, it becomes minus t. We have to reorder the function sin 2t into sin 3t as sin 3t into sin 2t for simplification purpose. So 3t minus 2t is t, and 3t plus 2t is 5t. So using the formula sin A sin B equal to 1 by 2 into cos of A minus B minus cos of A plus B, we got 1 by 2 into L of cos t minus cos 5t. So 1 by 2 into applying Laplace transform for these two functions. Now this can be reduced into addition of terms. So what is Laplace transform of cos t? That is s by s square plus 1. And what is Laplace transform of cos phi t? That is s by s square plus 25. So after taking LCM and simplification, we got the result as 12s divided by s square plus 1 into s square plus 25. And very important, another one example for finding the Laplace transform for the function f of t equal to cos t on the range 0 to pi, and it is 0 for t is greater than pi. So we have to use the formula for Laplace transform. So by the definition of Laplace transform, we know that L of f of t equal to integral 0 to infinity e power minus st into f of t dt. Here our function should lie only in the range of 0 to pi. So we have to split the integration as 0 to pi, integral 0 to pi plus pi to infinity. Here we see that on the range 0 to pi, the function is cos t. So in the formula, integral 0 to pi e power minus st f of t dt should be replaced by cos t. F of t should be replaced by cos t. And for the range, for the second integral, the function should be 0. So it will be cancelled. So that our problem can be reduced into integral 0 to pi e power minus st cos t dt. So now we can integrating this function with respect to t, and after applying the limit 0 to pi, we got the result as s divided by s square plus 1 into 1 plus e power minus pi s. So for integrating this function, we use the formula integral e power ax cos bx dx. So what is the formula? E power ax, integral e power ax cos bx dx is equal to e power ax by a square plus b square into a cos bx plus b sin bx. So using that formula, we can easily integrating this function. After applying the limit, we get the result as s by s square plus 1 into 1 plus e power minus pi s. So these are the properties of Laplace transforms. First one is a linearity property. Linearity property, the statement of linearity property is if we are having two functions f of t and g of t. So here f of t and g of t are two continuous functions of t, and k is a constant. Then number one, L of f of t plus or minus g of t is equal to L of f of t plus L of g of t. Second one, L of k into f of t equal to k into L of f of t, where k is a non-zero. So here k represents a constant, and t represents a continuous functions of f, and g represents continuous functions of t. So this is linearity property, and second one is shifting property. First shifting theorem. The statement of first shifting theorem is if L of f of t equal to f of s, then L of e power minus at into f of t is nothing but f of s plus a. So this is the statement of first shifting theorem. So the proof of the theorem is followed from the basic definition of Laplace transforms. So the definition, we know that the definition of Laplace transform is L of f of t equal to integral 0 to infinity e power minus st f of t dt, which is equal to f of s. So therefore just to replace in the place of f of t by e power minus at. After that we can simplify, like we know that the product of if two functions or product in which the bases are same, we have to add the powers. So that here e is the base, so e power, just adding the powers, minus st minus at, it becomes minus of e power minus of s plus a t f of t dt. So this is equivalent to capital F of s plus a, or L of f of t, where s tends to s plus a. So this is the uh, first shifting theorem. Another one is if the function is L of e power plus at f of t, then the result becomes f of s minus a. So first shifting theorem is nothing but if the Laplace transform of the function is in the form of e power minus at f of t, then the result should be f of s plus a. And similarly, if it is L of e power at into f of t, the result should be f of s minus a. And another important property named as change of scale property. So change of scale property, the statement of change of scale property is if the Laplace transform of the function f of t equal to f of s, then L of f of t is equal to 1 by a into f of s by a, where a is greater than 0. So this the proof of this statement is from the definition of Laplace transform. Here we have to replace in the place f of t by f of at. And by introducing substitution, by using substitution rule, we can introduce a new variable as x. Just replace a into t equal to x. After that t equal to x by a, then we can differentiating t with respect to x, we get dt equal to 1 by a into dx. After that, the new limits are also obtained by putting x is equal to 0. By putting t equal to 0, we get x equal to 0, and by putting t equal to infinity here, we get x is equal to infinity. Therefore, the result becomes L of f of at equal to integral 0 to infinity e power minus s into, replace this t by x by a, and f of at by x and dt by dx by a. So, after taking simplification, we get the result of the Laplace transform of the function f of at is equal to 1 by a into f of s by a. Thank you.